Travis with Adams Corp here with Scott Howard today from Donaldson Hypro. I'm Travis Dorman. I've been with Adams for 17 years. I cover our fluid power division, and I specialize in hydraulic filtration and lubrication. With me today is Scott Howard. Scott, can you give us a quick rundown of who you are, who you're with, and what you do for that company?
Sure. Thank you for inviting me, Travis. I'm happy to be here. My name is Scott Howard with Donaldson Hypro. I'm about to complete my 23rd year. I'm the senior key account manager, also involved in teaching as well. So thanks again for the invite. Perfect.
With that, we've been with Hypro for probably about 10 years now. At some point, y'all changed and you became Donaldson Hypro. What happened in that change?
So May 1st, 2017, we were acquired by a Donaldson company, and that was a great acquisition. We were a very small company focused on industrial hydraulics. So now, officially as of a year ago, the name has changed to now Donaldson Hypro. We are the industrial hydraulics business unit within the company. They bring a lot of engineering expertise, also doctors that are in the lab that are working on new technology. It's fantastic. It's been a great partnership, a great marriage. So yeah, officially now Donaldson Hypro.
Perfect. Now y'all are looking at multiple different industries, right? When we're talking filtration, and in Florida we have tons of different industries. You know, we got the power industry down here, cement, sawmills. When you're talking about these industries, what are you trying to do to help these industries? What are you looking at?
Well, it's uptime. It's uptime, and that means component longevity. So what we focus on is mitigating and controlling the contaminants that are in lubricating oils, gear oils, hydraulic oils, and fuel oils. And so those are like the top ones. And the contaminants that we really focus on are dirt, water, acids, and varnish. And so those are the ones that we focus on in particular for mitigating and controlling, so that your component lifespan can be realized, and also your oil longevity as well.
Yeah, I mean, we're constantly, from an Adams standpoint, going out and talking with customers and looking at their particle counts and trying to understand, hey, what does this look like? And explain to them, how do you quantify how many particles you have in your system? How do you tell what that is? And we're doing the same thing you are. We're trying to educate those customers at the same time. So when we're talking with customers, about particle contamination, where should we really start? Like, where should that customer start his journey to total system cleanliness, I call it?
So the two questions that I always tell the customer that it's something that I like for them to ask of us. It's like our responsibility, and that is, how clean is my oil and how long is the filter element going to last? That's basically our focus when it comes to solid particles. We want to be able to maintain our ISO codes very low, well below the limit, and as a result, kind of talking about dirt makes dirt, clearance size particles, how long is the filter element going to last? Well, the cleaner you can maintain your operating ISO codes directly results in longer filter life as well. So what we have to do is we have to get control of the contamination in the system. So ideally, you want to have a system that's very isolated from the outside environment, and then be able to focus on internally ingress contamination. So that's the first thing that we like to talk to the customer about, is identifying what is the concentration of solid particles in your oil right now. Mm-hmm. And then let's look at the system and see how isolated it is or sealed up from the outside. Even if it's an open system and it breathes, we want to know how sealed up it is from the outside environment. And so we'll talk about those different forms of ingression and contamination that gets into a system. Then when we get it to a point where it's a very clean system, we can maintain a clean system. But the very first thing we need to do is identify how clean or dirty are we right now.
Agreed. So, the one thing that always makes me laugh is customers bring me a sample bottle and they go, hey, can you test this? And I hold it up to the light and I see chips floating around it. And I'm like, yeah, it's dirty. And they're like, well, you don't have to take it to a lab. And I'm like, no, we're not looking for stuff that we can see visually. So how do you like bring that up to customers? Because they look at me and they're like, oh, look, I got contamination. I'm like, yeah, that's not really what we're looking at. We're looking at the microscopic level.
That's exactly right. And if you consider components in the system, the components with the most limiting or the tightest clearances within their own, like for example, a control valve or a pump, the clearance size particle is the most damaging particle. So if you consider those high-end components, we're talking about particles that are very small, less than 10 micron, closer to maybe less than 5 micron, closer to 1 micron. Well, when we step back and think about that, anything smaller than 40 micron, the human eye, the unaided eye, can't see an individual particle that's smaller than 40 micron. And so we are trying to mitigate and control the contamination levels of clearance size particles that are much smaller than we can even see in a sample bottle or in oil. So yes, that's a very good first test, is hold the bottle up to the light and say, can you see any particles in there? And if so, okay, let's stop and let's have a conversation about this. One of the things I like to talk about is, how was the sample acquired? It's very critical. What was the method that you went to actually fill up the bottle? Where in the system did you actually acquire this oil sample from? Because we want to be representative as far as the sample bottle of what the pump is sending to the system, to the valve bank, or whatever the case may be, the cylinders. That's the most important part. We want to know what in the reservoir, what the pump is picking up, but more importantly, what is it sending to the system itself? How was that sample acquired? And kind of start that conversation.
Yep. Yeah, I'll have a picture up here that when you're thinking about micron size, I try and jog my customers' minds with what size we're talking about. Like a white blood cell is 25 microns in diameter, roughly. So when we're talking about 4, 6, 14 micron, like just think, a white blood cell, you can't even see it. The other thing that we always talk about is they're like, well, I flushed that system and I just put brand new oil in.
Right.
And so they're constantly telling me, I got all this new oil, Travis, and it's super clean. Well, the refining process, which you can probably explain, is dirty in itself. So I like to tell them that new oil isn't clean oil. So can you elaborate on that a little more?
Sure, absolutely. New oil is new oil. It's not been used yet. It's not in service. Mm-hmm. It's got its full additive package. If it has an additive package in it, it's new. It's unused. But oil is tacky. It's sticky. So once it goes from the refinery to the piping to, let's say, an 18-wheeler, a tanker, then it gets to a distribution center. The oil suppliers maybe puts it in totes and barrels. On average, oil changes hands around 7 to 8 times before it reaches the customer. It never is filtered in those processes of changing hands. And so it's still, it's tacky, it's sticky. Whenever it comes across loose contamination, it's going to pick it up and take it with it. So we always preach that you have to confirm your oil cleanliness levels before adding it to a system. And the tighter the clearances and the lower the ISO code limit is, and we'll get into that, what an ISO code limit is, but your system is going to have a limit for concentration of particles per milliliter. When we add top-off oil that's new, or even if it's been recycled and cleaned, we either can add oil that's dirtier or cleaner than the oil in the system or the limit for that system. We have a choice. So let's add oil that's cleaner so we're not bringing particles in that could potentially cause an issue long term, and you just don't want to add the concentration of particles. So keep that in mind. New oil is new, but it's not clean, and we need to take on the responsibility. And people ask, well, why isn't it filtered beforehand? That's a cost. And there are some oil suppliers that will filter it to a certain cleanliness level and provide that oil to a certain ISO code limit that you ask for, but that's an additional cost. And so it's not something that's generally brought up.
Yep.
So you have to take that responsibility on yourself.
Yeah, I think another thing to point out is I probably visit about 80% of my customers. And so when the oil supplier brings the oil in, it goes to their holding tank, but they have no filtration on it. So it's like it's sitting there breathing because the tank has to breathe, just pulling contaminants in. And it's like, okay, now you're going to go fill something up out of that after the oil supplier filtered it, but you haven't been maintaining it. Now you're going to take that oil and go put it into a system. It's like, you know what? We really need to put some side loop contamination prevention on that. You talked about ISO codes. So that brings up, you know, how do we quantify the dirt in a given oil spec? Do you want to, I know Scott's technically on vacation today, and he decided to come spend time and nerd out and talk about particle counts and varnish and different things with us. So do you want to talk about the way we quantify using ISO codes, what the dirt in a system is?
Sure. So ISO code, ISO 4406 is the international standards. International standards are created for repeatability throughout the world, regardless. And so what this is our communication. This is our language when it comes to contamination control in oil to quantify how much, as far as the concentration of solid particles that are in the oil per milliliter. Okay, so if you consider a standard bottle is around 4 ounces or 100 milliliters. An ISO code, you use a laser counter that then looks at the particles down to and including, down to 3 micron, 2 micron, 1 micron, and will categorize the particles into 8 different channels, 4 micron and larger, 4.6 micron and larger, 6 micron and larger, 10 micron, 14, and then there's some larger channels. Mm-hmm. The International Standards Organization has picked the 4, 6, and 14 micron channels to be able to give a consistent way of monitoring your oil contamination levels. So then the component manufacturers will then test their machines and be able to provide a limit using the ISO codes that we just spoke about, the ISO 4406, to say if you maintain your concentration at or below this limit, we expect our component to reach its full lifespan that we've designed it for. Yeah. And so that's how we look at it. When you collect an oil sample in a bottle and it goes to a lab or you process it on site, we're going to look at the particles per milliliter. Now there's an ISO code range, 4, 6, and 14. You see the 3 different digits, but that's a general range. We want you to focus on the actual particles per milliliter that's embedded within, that creates those ranges. So let's say, for example, 16, 14, 11 may be an ISO code limit for a servo control valve. Mm-hmm. Well, what's the range? If we're in the 16, 14, 11 ISO code, are we closer to the upper limit of that 16? Are we closer to the lower limit? I want to know the actual particle counts to be able to determine. But to answer your question, kind of a long way, it's the ISO 4406 lab report that's produced either locally or at your lab that gives you concentration of particles per milliliter of solid particles in your oil.
Yeah, I think that most labs now are giving you that ISO code, but then they're also giving you what particles they found within that code. So that gives you a better idea of where you are on the spectrum of those ISO codes. And one place I like to start with people on the ISO code to kind of, paint that picture is the 10 code. It's 5 particles to 10 particles.
That's right.
But when you go from the 10 and then you jump up to the 11, it's now 10 to 20.
Yep.
So you got to notice that the delta between those two numbers doubled. And so when you go from an 11 to a 12, it goes from a 20 to a 40. So it then doubled that one. So as you go up the range, it keeps doubling those numbers. What I also like to do with customers is take digital images of patches. So like, hey, I pulled a sample and I sent it off to my lab, and my lab came back with this. Big whoop. I don't really know what that means. Right. I'll go pull a sample with customers and run it through a patch and take a digital image and give it to them and go, hey, sir, you're 242219. Oh, what's that mean? Well, here's a picture of what that means. And it kind of sets that light bulb off in their head as to, wow, that's a lot of dirt. And then to tell them, well, your ISO code came from 1 milliliter. 1 milliliter there's 3,785 milliliters in a gallon. And now you've got that much dirt in 1 milliliter. Do the math. You got a 700-gallon system. It's a lot of dirt. You're putting a lot of contaminants through that system, and yep. We got to figure out how to get that out of there and get it cleaned up to like a 16, 14, 11.
Yeah, it's a good point with the patch because it's a visual. It's very, very helpful to also have a reference patch of this is what it should look like. This is what it does look like. It's very useful. I find whenever I collect an oil sample and I'll process it through a patch, typically on site for the customer to see right then, everybody wants to look at it. And now they say, oh man, that's unfortunate, but let me look at that again and see. And it really helps them connect the dots. It really is useful to then give the relation. What does this ISO code mean? Well, this is what it means.
Yep. So now that we found out how many contaminants are in the system, we're like, oh, geez, it's dirty. How do we pick the right filter? How are they rated? How are filters rated? How do I know I'm getting a good filter?
Well, you have to look at the beta ratio, and then you have to, I say, basically test it because the beta ratio is going to give you one aspect. So, for example, Donaldson High Pro is a beta 4000 for any particular size particle, let's say a 10 micron and larger, or 6 micron and larger, or 3 micron and larger. And so what that means, that's a ratio. 4,000, we don't put the colon and then number 1 after that, but it's a ratio, 4,000 to 1. What that means is it takes 4,000 particles of that size to enter the filter element before the one particle will escape or make its way through. It's not a perfect filter element because we have to allow oil through it.
Yeah.
So we have to balance that, allowing oil flow through it, but being able to capture the particles at a high efficiency, because your filter element in relation to your oil contamination levels will either do one of two things. It's only two options. It's either going to pull out the contaminant faster than it can be created or ingressed, or it's not.
Yeah.
And so you're either going to allow the system to get dirtier because you can't keep up with it, or you can get cleaner because you're more efficient and pull out and capture those particles faster than they can be created and ingressed. And so that kind of reminds me of, just to talk about the 4 different areas or methods for dirt to come into the system. You have built-in. Okay, we also have externally ingressed, and we'll talk about that. And then we have internally generated, and then maintenance. Well, the internally generated one is really, really critical. And what that means is dirt makes dirt. Yeah. As a clearance-sized particle gets in between moving parts, it gets work hardened. Then it will cause the internal surfaces of that component to start being chipped away at a microscopic level, and then maybe larger. Depending on the particle size, now you're creating more dirt. And so we need to be able to drive down the ISO codes low and be able to keep up with and pull out particles faster than they can be created to maintain low ISO codes. That's very important.
Perfect. Yeah, I agree completely. We get to customers and they start talking about filtration, and we're working with them, and they're like, well, how are these filters rated? And the beta ratio is great. It kind of puts everybody like, here's my apples to apples. But you said it best. Like, I want to put my filter in your system, and I want to show you cleaner oil. Like, if they can get you down to a 17, 15, 11, I want to show you that that's as clean as they can get you. I can get you even lower. And the lower I can get you, every time I drop the ISO code, the longer components are going to last in your system. So showing that, knowing that Adams goes out and does these types of tests alongside you guys where we show customers cleaner fluid with our filters, what are we doing to our filters? I know you can't go into all the secrets here. That probably wouldn't be fair to you, but can you give us some kind of idea of what you do differently that separates you from everybody else in the filter industry?
Sure, absolutely. So your filter should not be an accordion.
Okay.
That's something that I like to just throw out there for people to think about. An accordion is something that expands, contracts. Yeah. Well, the filter should not be that way because it will unload particles. Now, every filter element manufactured in the world unloads particles. So does Donaldson Hypro, but we feel like because of our extensive testing that we do in the lab and then in the field, that our unloading is significantly less than anything else out there. And why? Is because we do the best job of keeping our filter element from changing its shape whenever you have pressure fluctuations through flow changes. Yeah. And so when flow changes occur, you're putting more pressure or less pressure on the filter element, allowing it to move. If you allow it to move, then you are going to allow particles to be unloaded downstream. And so through our dynamic filter efficiency testing that we do and design of our filter element itself, and we do this intentionally to be able to say, okay, from the lab to the real world, when the real world puts our filter element through stresses, we want to be able to maintain operating ISO codes below the ISO code limit for that system. And that's why we preach, test our filter element, test the filter element that you choose to, or you think that it will do the job for you, because if it cannot maintain your operating ISO codes below the limit, then it's not doing its job.
Yeah.
And one of the ways that it can't maintain ISO codes below the operating limit, or operating ISO codes below the limit, is if it continues to unload. If it continues to unload particles, you're adding particles back to the system that have already been captured. And one other aspect of that I like to mention is that also will negatively affect your dirt load, your dirt holding capacity of your filter element before it's actually pulled out of the system. We use differential pressure indicators to determine, ideally, condition-based versus time-based. Ideally, you want to use differential pressure indicators to determine when we reach terminal differential pressure, pull the filter element out. Well, an unloading occurs, over 95% of the filter elements is outside to inside flow direction.
Yep.
So when you unload, you're unloading through the middle. That amount of particles that have been unloaded then comes back around to the outside and finishes face loading of the filter elements. Doesn't take as much particles to finish face loading on the outside for that differential pressure indicator to say it's time to change. So by unloading particles, the filter element does two things negatively to the system. Number one, it cannot control the operating ISO codes under the limit, and it also, in effect, causes the filter element to be pulled out of the system with less dirt holding capacity as compared to one that doesn't unload as much.
Yeah.
So it's really, really critical that the filter element can maintain your system cleanliness below the limit, and also that promotes longevity of the filter element.
Yeah, you hit on two good things there that I bring up with customers all the time. The proof's in the pudding. Like with Adams, with Donaldson, we'll give you free filters and prove that our filters are better than what you're currently using. And at the end of that test, if we've proven ourselves, then we like to walk down the rest of, let's look at the whole plan as a whole and start that walk down total system cleanliness. So I've had a lot of customers, they're like, hey, having a cleaner filter is great and we want to get there, but we want our filters to last longer. We want our TCO for filtration to come down. And with your dynamic fluid efficiency testing that you do, your filters in reality last longer because they're doing a much better job. So I'm able to talk customers in from being time-based filter changeouts to looking at differential pressure and showing them, hey, your old filters lasted 3 months. I can now push you out 6 months, 12 months, and give you a return on that investment for going to a different filter, which overall gives them a lower cost of ownership on that given system, which nobody's turning down these days. That seems to be the biggest question when we talk filtration is how can I push my filter elements out longer? So I think we've kind of beat particles to death. Let's move on to water.
One thing I want to mention on the particles before we move on to water is how clean is my oil?
Yep.
And how long does a filter element last? Just like you mentioned, those are the two questions. How clean is my oil? How long does a filter element last? There's a direct correlation. If I can maintain low ISO codes, and you'll notice the Donaldson Hypro recommendations are generally about 2 ISO codes lower than the component recommendations. And that's not to sell more filters. Yep. That's because if you can maintain a system even lower operating ISO codes, your filter elements will last longer because dirt is not making dirt in the system. And so it is real. How clean is my oil?
Yeah.
And how long does a filter element last? There's a direct correlation.
That's a great point. That is a great point. So moving on to water, the first question I get from customers outside of power industry, where'd the water come from?
Well, as we sit in this room right now, we have a humidity.
Yep.
Maybe it's 30, maybe it's 50% humidity. Outside is maybe 80% humidity. There's water in the air. Even in the desert, there's a humidity.
Yep.
And so there's water everywhere. Also, if you are using any type of cooling system that has water, there's a potential there. But air carries a lot of water in. Oil can also carry some water in as well. It can hold water. And so you have two mediums there. You have air and oil that can bring water into the system. Gotcha.
Now, when we're talking water, first customers are like, hey, my system's being a little spongy, but if I have water in my system, what am I looking at from the damage aspect? What's water doing in the system other than making my system spongy and erratic?
Well, it changes the viscosity of the oil, number one, and so that's critical because the number one quality of the oil that you look at on a lab report is how is my viscosity in compared to where it should be. And then from there, if it meets the, it's in the zone, then you can look at other parameters. The additive package, whatnot. But it's first viscosity. But water will cause oxidation to occur, and so rust. But also it will take down the additive package. If there is an antioxidant additive package, the O and the RNO, well, water is a contaminant. And so you're going to start depleting your additive package at a more rapid rate as well. But it really does have an effect on the internal surfaces of the system as well. It does not allow for the oil wedge and journal bearings, for example, the way the oil should be. Yep. The water does not provide for that. And so there's a lot of negatives with water being in the system. And so we have to address water.
Yep. Now, when water's in the system, there's 3 phases. So what are those 3 phases of water?
Well, dissolved is first. And so oil has a capacity like air has a capacity. We're 30% humidity in this room, for example. That means it's 30% full of dissolved water. Dissolved water is your first phase. Once you reach saturation, and saturation is directly related to temperature, so as the oil temperature goes up, its capacity to hold more dissolved water goes up as well. So once you reach saturation, any additional water that's brought into the system is considered free water. Now, if it gets blended with the oil, we call it an emulsified water. It's free water that's been blended with oil. So dissolved, emulsified, and free water. The most damaging of those is free and emulsified. Those are the 2 that need to be addressed immediately. So we always say that you need to pay attention to your dissolved water content because we assume that in a perfect world, we're going to remove all the free water and the emulsified water. So I believe it's the bearing life, L10 life testing that's done. It's 100 parts per million where the test is done, and that's to test to see if the bearing is going to last the lifespan that it's designed to last. Most oils have a saturation limit above 100. So that tells us right there that the bearing manufacturers are interested in dissolved water as well. Gotcha. We have a saturation meters that will monitor for dissolved water. If a saturation meter reads 100, then that means we probably or most likely have free water, maybe emulsified, but definitely free water in the oil needs to be addressed.
Yeah, so there's some rough testing that you can do. The relative humidity sensor in your system, always great to have, but there's also the crackle test and the Carl Fisher test. Those seem to be the two tried and true methods that most customers ask me about. Could you do a quick explanation on both of those?
Yeah, crackle test basically is a hot plate.
Yep.
So if you want to envision making a really hot plate like a pan on your stove and you drop oil in it, if there's amount of water, generally speaking, 200 to 400 parts per million is the lower limit for a crackle test. So if you have more water than that, when you heat up the hot plate and then you heat up the oil that's placed on the hot plate, the water will flash to steam. When it does that, it pops or crackles.
Yeah.
And so that's the indication that, okay, I have water. We don't recommend that for really dialing in your water concentration. Carl Fisher is what you mentioned. Now, that's a titration that's done at a lab.
Yep.
You can buy your own titration equipment, but people generally don't have that. So you send your oil sample to a lab, and through a titration, all the way down to single-digit parts per million, you can dial in exactly the concentration of the water in parts per million that's in your oil. And so, yes, the Carl Fisher, that's our preferred method.
Yeah, I like to tell customers, hey, if you think you have water, do the crackle test. That'll tell you, hey, I have water. And then from there, you need to send a sample out because
Right.
we need to know what's in there, how much, because that's going to help us sometimes determine what equipment we're going to use to remove it. Adams, luckily, we rent different pieces of equipment from Hypro to remove water. We also sell it as well. But walk me through those types of equipment.
Okay. Yeah, we have water absorbing filter media, so we can put water absorbing filter media in any of these, for example, or any of our products. That's a consumable that's only addressing free water. If you have a very, very small system and you have a filter cart, for example, you can tell us, this is the filter element that I would like to use. Here's the volume of oil in the system. This is the assumed water content. If it's not assumed, if it's known, it's even better. And then we can give you an idea of how many filter elements that you plan to use will be needed to pull out that free water. But that is a consumable and can be the most expensive way to pull water out of a system on larger systems. It's also limited to just free water. And then you look at coalesce technology and vacuum dehydration. Coalesce technology will be limited to turbine oil, compressor oil, and fuel oil. Those are on the thinner oils. So turbine oils are typically an ISO viscosity grade of 32.
Yep.
And then compressor oils may be up to an ISO viscosity grade of 100. And then fuel oils like diesel would have a viscosity typically around 7 centistokes. That's very thin. Those are where we'd recommend coalesce technology. A word of warning. Anti-wear additive package and extreme pressure additive packages will adhere to the coalesce media and render it useless. So this can only be used on oils that have either no additive package or just a rust and oxidation inhibitor additive package, i.e. the turbine oil and the compressor oil.
Gotcha.
The limitation with coalesce technology is free water only. So we basically, what I like to say is 130 Fahrenheit is where I like there to be the fulcrum below which coalesce technology is more effective, even though you can use it above 130 Fahrenheit. Keep in mind, the higher the oil temperature is, the more it can hold water in a dissolved state. If water is in a dissolved state, coalesce technology does not address it. So we say for most effective use of coalesce technology, we ideally want you to put it on the system that operates under 130 Fahrenheit. Obviously, for fuel oil, it's going to be at ambient temperatures, so that's perfect. It's great for single pass water coalesce and separation. Free water, we can see a significant stripping of free water in one pass, which is great. But it is limited to free water only, and it's limited to thin oils and also the additive package. So keep that in mind. Beyond that, vacuum dehydration really is the best. It's the best because it does not matter the viscosity grade of the oil, ISO 680, ISO 1000 if you have it, which is rare, but it's out there. But anything under that, free water, all emulsified, and dissolved water. So what we do with vacuum dehydration is and it doesn't matter the additive package. So we heat the oil up and we pull a vacuum. So we flash water to a vapor at a temperature that's not 100 C or 212 Fahrenheit, which would be detrimental to the oil. Yep. So by pulling a vacuum, creating a vacuum on the oil, we can flash water to a vapor at a much better temperature for the oil, 150 Fahrenheit, for example, maybe 140. And it all depends on the vacuum that you can pull on that system, what the system will allow. What I always say is go as high as temperature as will be allowed for the system and the oil, because then you can use lower vacuum, and the vacuum translates to airflow, and airflow is how you pull your water out. But the technology of vacuum dehydration is very simple in theory. You're going to draw a vacuum on the oil, so we pull oil into our vacuum dehydrator, and then from there you heat it. And when you heat it and you go through these dispersal elements like this one shown here, we're going to break up the surface tension of the oil. And by breaking up surface tension of the oil, it allows the water to be released and switch to a vapor much easier versus if we didn't. So it's a faster operation. Vacuum dehydration can get your water content down to less than 50 parts per million and potentially less than 10 parts per million based on your application. So that's the one that we recommend. There is another technology called a headspace dryer. And so this is where we direct super dry air across the top of the oil inside a reservoir. Take, for example, a gearbox. You've got a certain amount of oil in your gearbox. If you have a small dry air purge going across the top of it that's super dry, nature tries to reach equilibrium at all times. It will release that water that's dissolved in the gearbox into the air, and as the air exits out the system, it takes the water with it. So that's a very, very good technology. You can use a headspace dryer for multiple gearboxes. You just put a airflow regulator, a flow meter on top. We say it's a positive air flow, but not a positive air pressure, because the flow is so low, less than 1 CFM. Yep. Not ideal for recovering a system fast that has an ingression event, but ideal for maintaining a very low water content. And then the last thing I want to talk about is a trap breather. That's the thermal reactive advanced protection. Mm-hmm. That is a type of breather that was created by Donaldson that is available. It's very useful, and it's significantly less expensive than desiccant technology. It regenerates. So as air is brought into a system, the water is trapped on the outside of the media, and then as the air breathes out, or if there's a differential temperature and the air is pushed out, the water falls off the trap breather and can be regenerated and used multiple times. So the initial cost compared to a desiccant is cheaper, and it lasts significantly longer, and it is as effective or more effective than desiccant when it comes to keeping the water in the air out of the system. So that's a really quick rundown. So just to review, water absorbing, contact Travis, for example, have your customer contact you and say, here's my situation. You can help them decide if that's the way to go. Or if it's not, coalesce for those turbine oils or compressors or fuel oil. I really like it for fuel oil. And then vacuum dehydration, which I think is the best technology there is because it can handle every oil. Your headspace dryers, and then also the trap breathers.
Yeah, and I don't think our customers need to know, what piece of equipment they need. Need to know what's out there and be educated enough that when they do call us and we start looking at oil reports with them, because we always ask for the oil reports, that they understand why we're picking what we're picking. That there's going to be certain criteria, like you had mentioned, that it's going to make me go coalescer. headspace dehydrator or vacuum dehydrator. The other one, I'm going to throw you a curveball now because I didn't talk to you about this before. But so vacuum dehydration, from my understanding, I've only been doing this 17 years. But from my understanding, previous to Hypro's dehydrator, vacuum dehydrators were very finicky. There were lots of knobs and buttons and things you had to get just right to get them to work. Well, as technology has advanced and, PLCs have gotten smarter, we're able to make these things almost down to like a one button push, set the vacuum level, set it and forget it and walk away. I got customers who still want to talk about centrifuges.
Right.
What is the difference in a centrifuge and a vacuum dehydrator? Why would we choose the vacuum dehydrator over the centrifuge? Now, the centrifuge was great 30, 40 years ago, but now moving into, 2026, next year, if I'm looking at removing water, why would I pick this over that?
Well, the first thing that comes to mind for me, based on my own experience, is maintenance. It's maintenance intensive, whether you have the stacked discs or the perforated tube type of centrifuge. It is maintenance intensive because you have to clean it because it's spinning at such a high speed. Any of the sediment that's slung out is caked up against the internals of the wall of the centrifugal purifier, and so maintenance is a bear. It is maintenance intensive. It's also limited. So particles less than 10 micron, generally speaking, aren't really separated, even in a centrifugal purifier, because of the lack of mass. There's just not a lot of mass to really separate it out. And then for water, below 1,000 microns, 1,000 parts per million, below 1,000 parts per million, doesn't seem to be really that effective on removing the water that we need for it to remove. So there's still some free water that's remaining if you use a centrifuge. So there's 3 reasons why. Oh, and by the way, it's just as it's not any cheaper than a vacuum dehydrator. It may be more expensive. So your cost, there's no benefit on cost. It's maintenance intensive. And if you know anybody that's worked on them, ask them, and they'll tell you it's maintenance intensive. You have to clean it all the time. And then it's limited with the particles in the water that it can remove. So it's okay. It doesn't do what we need to do in 2025.
They're generally slower flow too, correct?
Correct.
Yeah, they're not, and we get up to, we're doing 100. So 100 gallons a minute with vacuum dehydration. And, most of the ones I see in the field are like 2 to 4 GPM. So it's like, how quick do you want to remove that water?
Right.
So now we'll transition to what I like to call the coolest part of my talks with customers, and that's varnish. Varnish has become the buzzword over the last 15 years. Customers call all the time and, I got varnish. And I get out there and it's like, okay, what are we really talking about here? So can you give me a quick, what is varnish?
Varnish is an oxidation byproduct. And in its infant stage, when it's just being created through either heat or a chemical interaction, we call it an oxidation byproduct. It's polar. So what happens is the oil has what's called solubility. It's like the capacity for oil to dissolve water. It also has capacity to dissolve oxidation byproduct. So when oxidation byproduct is created, the oil will dissolve it. Mm-hmm. What happens as a result is the antioxidant additive package tries to neutralize this contaminant, this polar contaminant that's now in the oil, and it starts to deplete more rapidly. The oil has a saturation limit. Once you exceed that saturation limit of oxidation byproduct, it's not dissolved anymore. Any newly created oxidation byproduct is now free floating in the oil, and it's polar, so it starts to attach itself to internal surfaces, like metal surfaces, inside a heat exchanger, for example, and inside the tank. And when we can see it, when we can actually put our eyes on it and see the discoloration, we call it varnish. It's basically a buildup of oxidation byproduct. So
bathroom ring.
Yeah, bathroom ring inside the tank. If you look at a heat exchanger, for example, it's a great insulator. A 1 millimeter layer a thickness of oxidation byproduct, or now called varnish, inside the heat exchanger is a 10% reduction in the efficiency of a heat exchanger. So that causes issues. Now we can't cool our system enough, and heat may be the reason why we're creating this oxidation byproduct to begin with, and now we can't maintain a cooler system. It gets hotter, kind of feeds on itself. Varnish can be an issue.
Gotcha. Yeah, we see it in power plants, so steam turbines, combustion turbines, but we're also seeing it outside of that now. We're seeing it in gearboxes. We're seeing it at extrusion molders. So plastic extrusion molders are having issues with varnish these days. Outside of the cooler, we see it a lot. It's tacky, so it sticks. Right. It slows flow down. Is there anything else that Hypro's seeing that's causing issues when we see varnish in a system?
Well, you do. You see that where you lose your ability to keep moving surfaces apart from each other. So it's like a servo control valve. If varnish starts to form internally between those moving parts. In a power plant, for example, if everything is operating correctly, the servo control valve is really not moving much. Mm-hmm. And so this tacky contaminant that starts forming on the internal surfaces can adhere itself to inside the servo control valve and be stronger than the capability of the actuators basically to move the servo control valve. Yeah. So then if it can't move, we have a unit trip condition with the power plant. And so you can see issues within a gearbox. It starts affecting the bearings. It also on the gear teeth itself. Generally speaking, it's just a problem that is heat related or chemical related. Now we can remove it, but that is something that needs to be addressed.
Okay. How are we, so unlike particles where I can just pull a sample, send it to a lab, they run it through a laser, how are we testing for varnish? What's that protocol look like?
Well, you have to collect an oil sample, and then you have to heat it up for a certain amount of time and then let it cool. That allows the oil to go through the dissolving of the contaminants and then letting the excess oxidation byproduct be released. So then you go through what's called a membrane patch colorimetric test. So you can see the color, which gives you the potential for varnish related issues. It's not a guarantee that you will or won't, but it's a number. So we use a photospectrometer to be able to shoot a laser through a patch. Once we have oil that's been pulled through the patch, and it gives it a number based on how dark the patch is. So that number correlates with the potential for varnish-related issues. There's also a ruler test, remaining useful life evaluation routine, and that's where a lab will compare the additive package to the original spec of that oil and determine, okay, how much remaining useful life with your additive package do you have left? On average, we would say in a perfect world, we'd like less than 5% of your additive package to be depleted a year. But we've noticed in power generation, for example, we see that number 20 to 30% in worst case scenario on an annual basis. So the way that the power industry generally operates is when you have depleted 70% of your additive package, you have 30% less left. It gives them a year to budget for new oil to be added to the system or to replace the oil in the system. But if you're losing 20% a year, that's a 5-year lifespan. I mean, that's it. Yeah. And so if you're losing only 5% a year, well, then do the math. It's a lot longer oil life. And so varnish will have an impact on your additive package. It will cause it to be depleted a lot quicker. So the ruler test is a way to kind of get an idea of how fast you're depleting as you trend it every 6 months or once a year, however often you actually perform a ruler test. That tells you on trend wise how fast you're losing your additive package.
Gotcha. Yeah. So once we get through that testing phase, what are we looking at for solving the problem? Obviously you can dump the reservoir, clean it out, and put all new oil back in. We've talked about, new oil isn't clean oil earlier, but, theoretically we removed all the varnish because we took the oil out. So we should be good, right? So I hear a lot about system flushes. that customers are looking at. What are we looking at from a Hypro standpoint? How would we correct the varnish issue with Hypro?
Couple ways I'd like to look at it. One is the power gen industry or turbine oil rust and oxidation inhibitors. But first, I want to talk about the hydraulics and the gearboxes, the anti-wear, the extreme pressure. You have to test it to make sure that there's a resin technology that's used, and then there's a ultra high efficiency filtration technology that can be used. If you want to use the resin technology with those additive packages, you have to test to make sure that it will not be removed. Mm-hmm. And so that test has to happen to make sure that we don't remove the anti-wear extreme pressure additive package in those applications. The VTM media that we manufacture is submicron in high efficiency, and it will remove free-floating oxidation byproduct that's in the oil by mechanical filtration. You'll also see it form on the core tube and the end caps because it's polar and it starts to collect there. That's a benefit. That's great. But it is limited to the free floating. So for it to be most effective when the oil is cold and more of the oxidation byproduct is free floating and not dissolved, that's when it's most effective, but it's also very effective in operation. So if you determine that, okay, this additive package, we don't have a resin formulation to address that, use the ultra high efficiency filter media. On the turbine oil, we use both. Use the VTM media to initially clean a system, and also it helps maintain very low particle counts. So we have varnish mitigation and control. Skid would be like a side loop. Something that you can shut down and change filter elements while the turbine is operating. That's a perfect way to address your entire system cleanliness and an offline loop so that your inline lubricating oil filters, like your duplex for your journal bearings, can focus on what's generated in the line, and also your hydraulics, for example, if it's a combined system and your hydraulics is pulling from the same oil. Those filters can focus on what's generated in the line. So the varnish mitigation and control loop can do a good job of the solid particles. But the resin itself is really effective with turbine oil with just rust and oxidation inhibitor. What it does is it actually pulls the dissolved contaminant out of the oil. So the oil regains solubility. When the oil regains solubility and we pump it back into the system, it goes throughout the internals of the turbine, it will start to dissolve either free floating, if available, or even plated out varnish that's on internal surfaces, redissolve it into the oil. So a couple of the huge or very big cost-effective advantages of using a resin formulation for mitigation and control of varnish is on oil that is at the end of life, and you plan on changing out your oil and swapping it to new oil, you can avoid a high velocity flush, a chemical flush, if you have time. And we say that the resin formulation, the resin technology is very thorough, but it's not very fast. With a caveat, as soon as you add it to your system and start pumping oil through the resin canisters, you've stopped the progression of oxidation byproduct buildup. So you've stopped it right then. Now the process is cleaning the system internally. That takes a little while. Ideally, I would like 30 days, 3 months, 6 months, a year, depending on how contaminated the system is, to do a thorough cleaning of internal surfaces, but significantly more thorough than any type of high velocity flush or chemical flush of removing the varnish that's already plated out internally. We'll return a heat exchanger back to its original state, and then you're using your in-service at end-of-life oil to do this cleaning. When you put your new oil in, your additive package is not going to go through an immediate hit. No. Trying to scavenge and mitigate and control all the remaining varnish that's internally in the system. We've used the in-service old oil for the time allotted that we were allowed before the oil was replaced, to do a thorough cleaning of the system. So it's very effective, but it will save a lot of money on the high velocity and chemical flushes. As you know, they cost a lot.
Yeah, I think customers think I'm a used car salesman when I'm like, oh, you're going to dump this oil. Why don't you put my system on before you dump it? So let's clean it. That way, when we, if you want to dump it and then put my system on after it, I still got to clean up what's left in there.
Right.
Because there's still going to be stuff out there. And they always give me this look like, are you lying to me right now? Or you just want to make a quick sell? It's like, no, this is going to help you so much more by putting it on before you dump that oil. Like, give me 3 months and then do your flush. And it'll save you. It'll push the oil life out as well, correct? Right. I mean, you get another TCO there, total cost of ownership, because your oil life will be better longer.
Well, and on that note, you're talking about using the canisters, using the resin canisters to clean up in-service old oil. Mm-hmm. We're going to be able to tell you on the front side kind of what to expect. Yeah. Say, okay, you might need 2 sets, might need 3 sets. But compare that to $100 to $200 or more, $1,000, $250,000 flush and chemical flush and all that. Yeah. That's not complete. That's not thorough. So now you're spending hundreds of thousands of dollars on a flush that doesn't remove everything.
Yeah.
Whereas all I need is time. Just continue to operate your turbine. We've stopped the progression immediately. Yeah, it might cost a couple sets of canisters, which is significantly less than the hundreds of thousands of dollars in high velocity and a chemical flush in order to prepare for your new oil. And it's more thorough. So it is a significant cost savings.
Yeah, the varnish space is just blown up. It's become a topic of conversations at more customers now than 5 years ago. 5 years ago it was power plants only. Now it's everybody's talking about it. They're all seeing it. And it's interesting too to look at the equipment and the stains. That they look like coffee stains on all the equipment. And then once you get a system on there, the customer calls you ecstatic and he goes, everything's shiny silver now and it works so much better. And it's like, oh, well, that's kind of the satisfaction in the job. The last thing would be additive packages. So when I talk to customers and they bring up additive packages, it's weird because that oil came from the factory, blended the way it was supposed to be. I'm of the impression like I don't want to add something to my oil that wasn't blended from the factory the way they do their blending. Just how do you put it in? But what's your take on the additive package?
Well, that's a very good question because we do get this question a lot. And we do not recommend changing the chemistry of an oil that an oil manufacturer has refined in their refinery and prepared for use. So I agree with you that that's something that we don't want to play in the messing with the chemicals field. But let's say your customer wants to try it anyway. Well, here's one of the things I like to mention. An additive package, a re-additizer, for example, what you're doing is you're dissolving free-floating oxidation byproduct and maybe even dissolving some varnish that's on the internal surfaces. And where is it now? It's still in the turbine. So it may be dissolved within this additive package, but it's still in the turbine. With the resin canisters, what we're able to do is we're able to pull this oxidation byproduct out of the oil, and then when that resin canister reaches end of life, you pull that canister out and put a new one in. Your oxidation byproduct and your varnish is being pulled out of the system. So we're not hiding the varnish so that it can't do as much damage, but it's still there. We're actually removing it from the system. So we do not promote re-additizing because we do not believe that we would be interested in changing the chemistry of the oil that the manufacturers have designed it for, but also the concept that you're not taking it out of the system. It's still there. And so there are other aspects of re-additizing, some other negative aspects that can happen, like foaming and whatnot once you reach a certain concentration, potentially.
Yeah.
But the one thing that we like to center on is it hasn't been removed. It's only been hidden.
Yep.
And is that hiding temporary? Is that permanent? Whereas the resin canisters, we're actually pulling it out of the system for good.
Yeah, I'm not a chemist, and I don't try and pretend to be one with customers, but I will say most of the time I get a call after they've done an additive package, and they're like, yeah, it got rid of it for, 6, 12, 8 months, whatever. And they're like, now it's back again. And so I guess it's kind of like that old saying, you're just going to kick the can down the road, but eventually you're going to have to deal with it.
Eventually you're going to have to deal with it. Yep, exactly. And so then what do? Well, you can go with the resin canisters then, or you can go with a high velocity flush followed by resin canisters. But you see a theme here. Eventually if you want to pull it out of your system and clean your system internally to what it looked like brand new, you really need to embrace the resin technology.
Perfect. So, Scott, we've talked a lot about different technologies that Hypro Donaldson has to offer. Is there something that if a customer is watching today and they want to learn more about total system cleanliness, what can we offer them?
Well, I think the first thing that comes to mind is a lunch and learn. So Donaldson Hypro with Adams Corp, we can come on site to a customer and we can have a very technical training session with questions and answers specific to their application over a lunch. And then we can take it out into the site and look at their systems and we can address problems that they may be having and help them come up with solutions that day. So we can get very specific with a customer that would like to take this to the next level.
That's a great idea, and we're not limiting to lunch. We like breakfast as well. So if you're needing a couple of minutes and you don't want to waste your guys' times when they could be out in the field, the lunch break, breakfast break is always a good time to try and get some education in there.
Absolutely. Yep, totally agree.
That does it for me today, Scott. Really appreciate you coming by and sitting down with us. Hopefully, if anybody needs anything, just reach out to Adams. We'll be more than happy to send one of our local guys out, or I can come out sizing equipment and hopefully bring Scott out with me sometime. So,
well, thank you very much. Thank you for the invite. It's a wonderful partnership that we have here. You guys are amazing at what you do, and we appreciate being a part of this podcast today.